So what are some of the advantages and disadvantages of each of these formats? So let's do a nice table. Are there easy intuitions? Well, for rotation matrices, we have excellent intuition. We know that the columns of the rotation matrix represent the new orientation of your axis. So if you just look at a rotation matrix, you immediately have a sense for what rotation it represents. This is very intuitive. Axis angle, also very intuitive. Somebody gives you an axis and an angle, you immediately know what that rotation means. So that's also easy to understand. Elementary rotation, roll, pitch, yaw, for example, Euler angles. If somebody gives you a roll, a pitch, and a yaw, especially if it's a domain you're familiar with, then yes, you know immediately what rotation that represents. Quaternions, on the other hand, there's really no good intuition. If somebody gives you 4 numbers and says this is a quaternion, this is a rotation, it's very hard to know just by looking at those what rotation they represent. So quaternions are hard to deal with for humans because of that. That's one reason why in this course we use a lot of rotation matrices. We have very good intuition for them. How do you chain multiple transforms? If you have 2 transforms and you want to chain them together, 2 rotations that you want to chain together, very easy to do with rotation matrices. You just multiply the 2 matrices. With axis angle, it's complicated. It's not very clear. If I give you 2 of these and say you have to do one followed by the other, how do you obtain the equivalent transform? Depending on which axes are chosen for the Euler angles, it can be easy or it can be hard. For quaternions, it's very easy to chain them because you just multiply the 2 quaternions together. So this is very, very easy to use as well, very easy to perform the multiplication. Okay. How much memory does each of these representations use? Well, for the rotation matrices, you have to store 9 numbers. For the axis angle, you have to store 4 numbers. For the elementary rotations, 3 angles, and for the quaternion, 4 numbers. So obviously, the rotation matrices are the most wasteful when it comes to storing them in memory. This day and age, computers have so much memory that it may look like, hey, that's not really that big of a deal. But still, almost twice as big, more than twice as big as storing a quaternion memory. So once you're dealing with, if you have to store millions of transforms in memory, then it starts to make a difference. And then finally, just from a numerical perspective, which of these are preferable? Rotation matrices, you keep multiplying them, computational errors, rounding errors accumulate, and then soon you end up with something that's no longer a rotation matrix, it's no longer orthonormal. And ultimately, so the rotation matrices are not ideal from a computational perspective. Quaternions, though, are excellent from a computational perspective. As the error accumulates from rounding, from floating point errors, it has desirable properties in terms of you are still close to representing an actual rotation. So if you look overall at this picture of advantages and disadvantages of various rotation representations, matrices are great for humans to look at, and we're going to be using them a lot. Quaternions are great for computers, where you don't really care about the intuition, but these are all very, very desirable, right? So most computer libraries that have to deal with rotations, transformations, will store them as quaternions, will pass them around as quaternions. That is sometimes annoying, because just by looking at a quaternion, again, it's very hard to understand what's going on. But remember that any transform library worth its salt will give you functions to convert between all of these representations. And this brings us to our final point, which is also a very important one. Ultimately, how many numbers do you need to uniquely define a rotation in space? Because you see, all of these representations use a different number of numbers, right? A matrix is 9 numbers, axis angle is 4 numbers. How many intrinsic, what we call degrees of freedom, are there? How many variables do you need to uniquely specify a rotation in space. Let's look a little bit more careful at these representations, right? A rotation matrix has 9 numbers, but they are not independent because the rotation matrix is orthonormal. So once you specify a subset of these numbers, all the others can be derived automatically because the matrix is orthonormal. The axis angle, that's 4 numbers, but again, these 4 numbers are not independent because the axis is normalized. The axis just specifies a direction in space. The magnitude of this vector is meaningless, so usually when you represent a rotation as axis angle, the axis component is normalized. So this really is only 2 independent variables plus the angle. So this gives us 3 independent variables. The elementary rotations, the Euler angles, that's 3 variables, not much else to say there. The unit quaternion, that's 4 numbers, but again, they are not all independent because it's a unit quaternion. So really, it's 3 independent variables, and the 4th one can be derived from the fact that it's a unit quaternion. So you bring it all together, the answer to the question is 3. So this is very important to remember. Any rotation in space is 3 independent degrees of freedom. 3 numbers are enough to uniquely specify a rotation. Any rotation can be uniquely specified by using exactly 3 numbers. Some of these representations are redundant, they have more numbers than that, but fundamentally 3 numbers are enough to specify a rotation. So this brings us to a complete transform. How many numbers do you need to uniquely specify a complete transform, right? One way to represent a transform, again, is as a transform matrix. We know that the rotation part only really has 3 degrees of freedom. The translation part has another 3 degrees of freedom. So then a complete transform in space has 6 and exactly 6 degrees of freedom. So if I have 2 robots that are independent of each other and they move through space independently of each other, how many numbers are needed to uniquely specify the pose of one robot relative to the other? 6. There are 6 variables that define this change in position, and exactly 6. Now, some representations might use more numbers, like, for example, a transform, sure, is a 4x4 matrix, but a lot of that information is redundant. So this is important to remember. 2 completely independent bodies, the pose change between them, 6 variables, 6 degrees of freedom, and no more.